Hi everyone. Today let's talk about functional testing of micro-optics for automotive. Before doing that, just a couple of words about Alfamation. We are an Italian company. We were founded 33 years ago, and we basically design and produce automated test systems across different markets, from consumer electronics to automotive infotainment, micro-optics and photonics. And we have now more than 130 employees, and we provided thousands of systems worldwide. And from the beginning of the year, we are part of Test Corporation, which is a larger American company which helped us increase our network globally even further. What do we do at Automation? We have multiple platform and test solutions. These are just some examples, starting from this Hyperion platform, which is really versatile, testing anything from antennas to infotainment system and audio amplifiers. We have a Flex Media XM product line, which are basically standalone test models, which are operating system independent, powered over Ethernet, which can do many things from audio and video generation and analysis to camera simulations. We have a platform for battery management PCBA test, an entire product line, a pixel shooter dedicated to the test of displays, for example in the automotive industry. And then we have our wafer level optics tester, the World platform, which is the platform where we test micro-optics at wafer level, and the platform that I will be talking about today. I wanted to talk about functional testing of micro-optics, and I wanted to try and answer this question. So what makes a good automatic test equipment? And I'd like to try to answer this question by starting from the manufacturer's perspective. So I think that for micro-optics manufacturers, a key concern is cost optimization. That's true at every level, so also when choosing the test equipment, especially in micro-optics where there's not necessarily a well-established standard to refer to, and there are multiple variants of the same product, different devices, shapes and sizes. Cost optimization is really important. And so that's why I think that a key feature of a test equipment is to achieve this cost optimization is modularity. So that's why we try to design our system combining different modules, starting from a base platform, in this case for wafer handling, a reading-based system, which is then combined with multiple track options where the wafer is loaded with different shapes and sizes, but also additional functionalities like wafer voltage compensation or vacuum retention. And then we have a set of configurable instruments which define what is the function of the device that we are going to measure. So it can be a set of conoscopes to measure refractive optical elements or metal optical elements used in consumer electronics for face recognition, gesture recognition, or microscope lenses for the test of graphing optics in telecom applications. And so then you have your fully configured setup that you can see in this small animation there. And this is a huge advantage, this approach, because a well-established platform lets us concentrate only on application challenges and also reduce costs by having a common base of components and spare parts and a system that requires less maintenance. And also I think it's interesting for manufacturers to have the possibility to retool the test equipment once the project phases out, for example. But sometimes this is not enough because we need versatility also within the same configuration. And so that's why another key feature is flexibility. And this is achieved both at hardware level with multiple degrees of freedom to try to account for every possible product variance of the same device, but also with a powerful and also user-friendly software interface, allowing the test engineer or operators to set up new test recipes and test parameters autonomously without retooling. And that's why we designed our own test sequencer, which is called Supernova. And it's it's based on national instrument test standard. So another important aspect for manufacturers when looking at automated test equipment is for sure efficiency. A fast solution is needed, which is also at the same time robust, stable, and easy to and scalable, basically. So that's why another important feature of test equipment is an high throughput. In our wafer level system, for example, this is achieved with a fast and reliable positioning system. We have some graphs here with some performances. For example, for a step size of around 2 millimeters, which is a reasonable pitch on a wafer. You have an execution time which is just 90 milliseconds with a settling window smaller than 300 nanometers. But also the high throughput is achieved at software level by using strategies like parallel threads to reduce or remove overhead, even by algorithms, image processing or logging, but also with test strategies like batch logic, which allow you to avoid to repeat the same time-consuming task at each lens, thus reducing the test time without reducing the test code. And instead, in terms of stability and robustness, reliability is important, and according to Automotive Industry Action Group, if a measurement system variation is less than 10% of the process variation, it's then a suitable test equipment, and so that's why we perform GR&R procedures to make sure that our system always falls in this range of variation. And last, it's important for manufacturers to have test equipment that are easy to integrate in a mass production environment, so with all its challenges. So it's important to have production and compatibility, especially in micro-optics, and so this is achieved both with an operator-friendly user interface, so easy to use for the operator, but also promoting a reduced operator overload by being compatible, for example, with robotized automatic wafer loading units, and also automatizing serial number reading and alignment procedural function. In terms of communication with the plant, we have a network integration, and we always implement mass interface communications to be able to communicate with the plant the results of our tests and having insightful understanding of the process. And then in terms of clear room compatibility, we have ventilation and filter units to make it possible. So with all this in mind, I wanted to show you a practical implementation of a test setup for micro-optics that we did for on our platform. In particular for the test of MLA devices for decorative lighting. These are the elements that are designed to project a pattern to a target surface, which can be both outside the car, like in these examples for welcome targets, so decorative reasons only, but also to communicate driving intention, so for additional functionalities. But also to project, they also project sometimes patterns onto dashboard within the car. And so the first challenge when testing this kind of device is that the pattern projected is kind of big, can be up to 3 or 4 meters. And so to keep the test system compact, we introduced a relay lens system, which allowed to take an image of the MLA on a smaller camera sensor, which is also much closer to the MLA. And then this kind of distorted image obtained of the camera sensor can be transformed digitally to obtain the projection plane image, and this is done by Alfamation proprietary algorithm. And then on this projected plane image, you can extract metrics like the relative brightness, contrast, and sharpness of the transition, the presence of ghost images given by crosstalk of different MLA channels, and also chromatic aberration. And we reached very good speed, up to 2800 units tested per hour, with a very good repeatability. And another another challenge is that there are multiple different projectors with multiple different patterns and projection setup. That's why we have multiple degrees of freedom in this application, like the field of the sensor and the distance of the camera from the relay lens to take all of these product variants into account. But sometimes this is still not enough because sometimes the projection surface is not a plane, so it's not the street, but it's an arbitrary surface like a dashboard of a car. And so in this case we have within the same configuration we have the flexibility to change the testing strategy. So in this case we perform a trigger scan acquisition with the camera sensor to sample the focal plane obtained after the relay system in different positions, and then we stitch together the different images obtained with a proprietary algorithm again, and then we project the image on the projection plane. And of course this is a slower method with respect to the first one, but it has the potential to be flexible enough to adapt to any 3D surface shape of the to conclude, this is just a portion of Alfamation portfolio capabilities. We have a really strong engineering team, so we are able to supply and provide innovative automated test solutions, develop new test methods, not only at wafer level. As you can see, we have a solution also for the test of assembled modules with pick and place platforms or manual loading platforms. And as system integrators, we are always looking for new partners, so new instruments and new test methods to integrate in our platforms, and also for new challenges in micro-optics and photonics. And so, thank you very much for your attention, and please visit us at our booth. We will be happy to discuss with you then. Thank you.
Thank you.